computer. All right, kids, we're back. We're going to do some notes again, 26 through, I don't know, 40 something. This is a little bit of an extension from the first class, a little bit of a reminder. The electron orbitals, the first orbital has a maximum number of how many electrons can fit in. You should jot that number down. It should come right out of your head. If you don't remember, you can take out your periodic table and look at the atoms in the last column number or group number 18, the noble gases, and the first electron orbital, of course, only holds 2 electrons. The second orbital, you can again look at the table because the noble gases only have full electron orbitals. They hold the maximum number of electrons that can fit. The second orbital, of course, holds 2. First orbital is 2. Second orbital holds 8, so it's 2-8. Now, the third orbital is weird. With argon, you can see that it fills up with 8 electrons, and I don't have 18 fingers. The third orbital, though, with krypton, you can see, can hold up to 18 electrons. So that third orbital and the rest of them, 4, 5, 6, and 7, they can stretch. But the important thing is here, the maximum number of electrons in the first orbital is 2. The maximum in the second is 8. The third one can feel full up with 8, and that's important, or it can stretch into a larger configuration and hold up to 18 electrons. The noble gases only have full orbitals. So whatever electron configurations are in the noble gases, you can be confident to know those are only full orbitals. And we're going to get to what that all means and the implications of that later on. We're just getting some basic stuff. This is some practice. This is going to require some paper, and you're going to need your reference table, your periodic table. Find silver. How many electrons does it have? Silver, I'll let you look for it, but it's in group number 11, and it's in period number 5. The periods go across, the groups go up and down. So period 5, group 11. Hafnium, hafnium is in group number 4, period number 6, HF. It's half as good as any other element. No, that's not true. Hafnium is just kind of a funny name. It's not half, it's half. 16 protons and 16 electrons. You might need to hit pause to do these. Don't let me keep going. You might have to hit pause. Get the answers to these because they're coming, and you got to see if you can get them right. Don't just be hanging out waiting for me to give you the answers. The point is not to fill in the notes. The point is to fill up your head. So hit pause and figure out 27 and 28, and then I'll be waiting for you when you come back. Element number 16 has 16 protons and 16 electrons, and that, of course, is going to be S for super special. I mean sulfur and tungsten. Now, in order to do tungsten, this is kind of a pain in the neck. You have to go to table S and scroll all the way through it until you find the name tungsten. I'll give you a hint though. Tungsten is the English name for an element that was named in German, Wolfram. Wolfram sounds like a wolf, Hungry Like the Wolf, which was a song by Duran Duran. The Wolfman was played by Lon Chaney and his son, Lon Chaney Jr., in different movies in different years. Tungsten is letter W, and that makes it number, what do we got? 74. Okay, not too hard now, these questions. These answers should all be obvious, right? Silver's number 47. It's got to have 47 electrons. It also has 47 protons. Hafnium. Hafnium has a mass of 178. My hands, I just washed them a little while ago. Protons and neutrons make up the whole nucleus. If it's 178 is the mass and 72 are protons, what's left? 178 minus 72 is 106 neutrons. Element number 16, put your finger in the box. That would be capital S for sulfur. And tungsten is element number 74. Now, 74 means 74 protons and 74 electrons. Now, this is a really cool picture. I got this picture many years ago. I Googled silly photograph of people with fake mustaches. As it turns out, if we were to do a real quick, and I'm going to do this quick as I can, this is important, but we're going to go quick. We're going to do about, I don't know, 2,500 years of chemistry history, the development of the model of the atom. from the beginning to the end. And almost everybody who was a famous chemist had a great mustache. You can see I don't have a mustache because I can't really grow a mustache. Some people can grow a mustache, like these women and this man in the picture. They're very funny looking. Those are fake, obviously. They're just being silly. I actually can't really grow a mustache. Doesn't work too well. I'm not a famous chemist either, so I guess it's okay. But if I were a famous chemist, I'd probably have to get one of those fake mustaches. So we're going to do a lot of history. How do we know? Now, you know what the model of the atom looks like. We saw a little cartoon the other day. We had the little gold ball in the middle and the 3 little electrons flying around. That was a cute cartoon. The models of the atom through history. And this is important because how this all came about is pretty interesting. There's a bunch of Nobel Prizes in there and some crazy ideas, and we'll make fun of them in a good way. I mean, they were remarkably good ideas, I suppose, at the time, but we now know so much more, and we can almost laugh at the innocence of it, the silliness of it. But we have to think about hundreds of years ago, people were different than you are now. They didn't have Instagram and internet, and they didn't have teachers like me. They didn't have teachers at all. They were inventing this stuff. They were figuring it out on their own, and they were doing their best. So some of the ideas are a little crazy, but they all had mustaches. Now, in the beginning, about 2,500 years ago, there was a philosopher. His name was Democritus. And think about it. He wore a toga, he sat on a rock, people would sit around and he would just talk. He was not a chemist, he was not a scientist. They didn't even have science back then. He would just think great thoughts. And he said one day, similar to this, now I paraphrase, of course, but this is from history books. He said basically, if you take something and cut it in half like an apple, you cut it in half and you cut it in half and you cut it in half, the pieces get smaller and smaller and smaller and smaller. And at some point, he said, there would be a piece that is so small that you cannot cut it in half and still have an apple. It's too small. And that indivisible particle, that smallest piece of something, he called in Greek, atomos, which we translate, of course, to atom. This idea of having an ultimately small particle of matter called an atom has endured. This is it. This is, for thousands of years, chemistry teachers could walk in and say, students, stuff is made of atomos, or atoms, if we speak English. And then there'd be nothing else to talk about. Cut it in half, cut it in half, cut it in half. The smallest thing is called an atom, and science was done. Chemistry was a complete subject for thousands of years. It was just, that was it. Pretty cool. They made statues of him. This is a statue of Democritus. He's got a good mustache. We don't have any photographs of him because they didn't invent photography until, it must have been the 1700s. So we have statues of him, but he had a good mustache. Now, in the early 1800s, there was a fairly well-off man in England named John Dalton who said, there's got to be more to this. There's got to be more than one word to chemistry. And he was kind of bored. He was a farmer, and he was so smart that it wasn't that hard for him to take care of the cows and the animals and the plants. He said, let me go in the barn and I'm going to invent chemistry. And he came up with what's called the atomic theory. This is the foundation of chemistry. Now, you don't have to memorize it. You do have to familiarize yourself with it. We're going to write it down. There's a bunch of space. There's 4 parts, so don't write too big. You got to fit them all. I wrote mine down, just so you know, right here. I mean, you got to write some stuff. What's unbelievable is this is the early 1800s, 1808 or something like that. This is a long freaking time ago. This is not like Democritus long ago, but, you know, this was a long time ago. The man invented chemistry. And although the theory is imperfect, there's a couple of flaws in it you may not catch, but I'll point them out. And I feel embarrassed to say, oh, look at me. I'm going to point out the flaws of John Dalton. This is one of the smartest people to ever be. And so we really, this is the foundation of chemistry. This is really important. There's a picture of him. Well, it's a picture of a painting. I don't know if that's, I don't think it's a photograph. But anyway, later in life, he grew a mustache. This is an early photo. Atomic theory. He said, number one, all elements are composed of individual kinds of atoms. And what does that mean? That means if you have some nickel metal and I have some nickel metal, your nickel metal is made up of atoms of nickel, and so is mine. And if you have a pile of lead, a hunk of lead. Lead is made of different kinds of atoms. Each element is made of one kind of atom. Number two, he said, all atoms of an element are identical. If I have some copper atoms and you have some copper atoms, my copper atoms and your copper atoms are exactly the same. And he didn't know a lot of chemistry. He didn't know anything about protons, neutrons, electrons. He didn't know anything. He was inventing this and making it up in a sense. He said that atoms of copper and atoms of lead have a different kind of mass, different mass. And that's true. You can look on your periodic table. Copper, remember, 64. Did you listen to that song yet? When I'm 64. Copper has a mass of 64 AMUs. He didn't know that number, but he knew that it was less than the mass of lead. He knew that all atoms had an individual kind of atom and they all had a different kind of mass. Now, what he kind of didn't understand was why they had different properties. Why did different elements? He said, well, they have different masses and the mass difference was enough to make all the properties different. A little dicey on that, but right? All atoms of one element are made of one kind. All atoms of one element are identical, all right? And different elements have atoms that are different masses. That's true. Now, number three, you can mix atoms together. Anybody could have said that, right? Just take your stuff, put it in a bucket, shake it up. It's a mixture. That's not so big deal. The second part of this is beyond genius. Luckily, it's right, because otherwise chemistry would be very hard. But because it's not wrong, it actually is easy. He said that atoms can chemically combine with other atoms in simple whole number ratios to form new substances. Now, let's just think of one simple compound that you're very familiar with called water. Water has a formula of H2O. There are 2 hydrogens and 1 oxygen. It's in a 2-to-1 ratio. It's in a 2-to-1 ratio, but it's not in a 4-to-2 ratio. 4-to-2 is the same as 2-to-1. It's the same proportion. Or how about 10-to-5 or 100-to-50 or 1500-750? No. It's not just in a 2-to-1 ratio. It's in a simple whole number ratio. It's literally 2-to-1. So when atoms combine, for instance, in this case, hydrogen and oxygen combine to make water, it takes 2 atoms of hydrogen and 1 atom of oxygen bond together to make 1 molecule of water. It's not just proportional, it's simple whole numbers. There's no half atoms, there's no decimal atoms, there's no giant multiples like H100O50. H100O50 is in 100-to-50 or 2-to-1 ratio. That's not going to work. Each water molecule is in a 2-atom hydrogen, 1 atom oxygen bonded together. This, how brilliant. Now, also, this fourth part is also genius. When atoms chemically react, this changes their arrangement to each other. Instead of being a pair of hydrogens and a pair of oxygens, you get together with 2 hydrogens and 1 oxygen, they bond together in a certain ratio. It makes a new substance that has all new properties, but when it's bonded together as water, it doesn't become something new in a sense. You still have 2 hydrogen atoms and 1 oxygen atom in there, and you can get them back. They come back. When they're bonded together, they act differently than they did when they were separate. Oxygen and hydrogen both have their own properties. Water has different properties. But you can take them back apart and your atoms don't change while they're bonded. They act differently, right? But they are the same. They come back and you can have them back with their original properties. This right here, this one slide, this is the beginning. This is it. This is chemistry. And from this, there have been many experiments to try to figure things out. Now, he said, John Dalton, when he wasn't farming and he wasn't in the garage, he used to go to the club and he used to play a game called billiards. Now, billiards on the bottom right there is a table called the carom billiard table. It looks like a pool table, but it has no pockets. Now, in the middle on the bottom, there's a regular pool table. There's 15 balls, 8 ball in the middle, there's a cue ball, there's sticks, there's holes, you got corner pockets, side pockets, you shoot the balls in the holes, you call them. If you play well, you call them. If you're just blasting them, you can still have fun. But he didn't play that game. Pocket billiards came about later on. There was the original table, was just flat and it had bumpers, and you played with 3 balls. There was your white ball, my white ball, and one of them would have a little circle painted on it so I could tell them apart. And there's usually a red ball. And the trick was, or the game was, you had to hit your cue ball into the red ball, and they both had to hit the bumpers. And then you'd have to leave the balls in such a way so that the next person, the other guy or the other person, the other woman who was playing, had to try to hit their cue ball into the red ball, but you try to park your ball in the way and block them. And you'd score points or not score points every time you did it. So it was more of a game of setting up the balls rather than knocking the balls into the holes. This was more of a strategy game. You had to be able to hit the balls and then block the other guy. And then he would try to hit the balls and block you. And you'd keep track. And it was a skillful game. And it was built on a table, like a pool table, but no pockets. And the balls, even like that 14 ball, right? 14 balls striped, and 14 is what? Silicon, the atom silicon. You only played with 3 balls. 2 white balls, one had a little mark on it so you could tell them apart, and 1 red ball usually. He used to play this game called billiards. Now, regular pool is not billiards, but sometimes people call it that, billiard hall, but nobody plays billiards. Not too many people play billiards anymore. They play pool. But he called this the billiard ball model. He said, I think, what does an atom look like? It looks like a billiard ball. It's a solid, hard sphere, and all the atoms of one element have the same mass, and all the other elements are solid little hard balls, atoms, that have a different mass. That wasn't really right. But he's the father of chemistry, right? He came up with the atomic theory. If there was a Nobel Prize back then, he would have got it, right? It didn't come about till later on. Genius, kind of a silly name for his atom model, but he thought they were little hard balls, and they kind of are. They act that way in a sense. They're not like billiard balls, though, or pool balls, but that's in your mind, billiard ball model. Next, look at this mustache. First of all, holy smokes. This man looks like he lives in the Bowery in the 1940s. He looks like a bum in the street. This man is Nobel Prize winner. Holy cow, J.J. Thomson. Mr. Thomson did a whole lot of experiments with something something that is called the cathode ray tube. Now, that's a vocabulary word. You don't have to really understand it. There's a picture of it down there, but basically it was a big piece of glass, a tube, a sealed tube that was like a vacuum. And on one side, on the left side there, you could shoot out electrons in a ray. You could just shoot them out, and it was electricity. And in the middle there's something called a deflection region. And what they had was 2 plates, top and bottom, and they would run electricity through one and no electricity through the other. And they push the electricity onto the plate on the top. And a lot of electrons, a lot of electricity would be built up on one side, and that side would have a lot of negative charge because the electricity was negatively charged particles called electrons. On the bottom plate, the electricity wasn't there. It was high amount on the top and very little on the bottom. So relatively speaking, the top plate was negative and the bottom plate was more positive. Now, if you pushed hard enough with enough electricity, it could spark across and it would arc across and electricity would flow. But in this tube, you could create a negative and a positive charged metal plate. Now, in the dark, if you shoot a beam of electrons, a beam of electricity through this, the beam would bend towards the more positive plate. You know why? Because the electrons that are coming through this vacuum are more attracted. They zoom in fast, but they're going to be more attracted to the bottom plate. And then he said, aha, this beam of particles, they're going to be called electrons. He discovered electrons. And he said they're negatively charged. So honestly, funny looking man. There's no getting around it. Look at him. You wouldn't want to live next door to this guy. Holy smokes, was he smart. In 1897, he discovers the electron. And he used this fancy tool called the cathode ray tube. Now, he called them corpuscles. It's a little too biology, so the name gets changed later to electrons. All right? And you can look at this. It's kind of a fancy schmancy kind of thing. You have to know the name. The name is often on the regions, cathode ray tube. You don't have to understand the mathematics or the physics or anything like that about this. But basically, he discovers the electron and he discovers that it's negative. He knows there are atoms, Democritus said atoms, and science believes that there are atoms. Dalton said there are atoms, and each atom has a different mass. Each atom is made up of atoms that are, each element is made of atoms that are identical, and they're neutral. He knew they were neutral. He's got this part of an atom called an electron that's clearly negative, but the atom is neutral. How is he going to put this together? How is he going to have an atom that's neutral but has negative parts? Well, it has to be balanced, I guess. There must be positive parts. What parts are they? He didn't know. He didn't. He discovered the electron. He didn't discover everything. He doesn't know everything in the world, but he discovered the electron. So he comes up with the crazy idea. His wife used to cook him lunch and dessert every day. And one of his favorite desserts was called plum pudding. Now, plum pudding is a weird thing. Nobody eats that anymore, but this is what it was. Basically some cake. And she would take some plums and she would chop them up in little pieces and roll them in the dough and bake them. And they'd come out in these like balls. And you could cut it very nicely like this one's cut. You could rip it apart. It was like kind of a big donut with no hole, like a softball sized dessert, right? Chopped up plums in cake with sugar. It was sweet. So if you cut it up nice, you could see the little specks of plum in the cake. And Thompson says, you know what? My wife is so smart. An atom literally looks like a plum pudding. Atoms are little round balls, and stuffed in them are these negative electrons, and all around those negative electrons is the stuff of the atom, and that's the positive charge, the positive mush. The negative electrons are embedded in. And each atom has a certain mass of stuff, and it has a certain number of negative electrons stuck in there, and the mass of stuff has an opposite charge that balances the electron charge. Now, think about it. This is, well, it's crazy. It's crazy. Had Mrs. Thompson made chocolate chip cookies for her husband, this model could have been called the chocolate chip cookie model. Look on the other side. I love chocolate chip cookies. You know why? Because they remind me of what atoms used to look like. Atoms have little chocolate chips. Those would be the electrons embedded in the positive mush of the atom. A chocolate chip cookie is an atom, and the chips represent the electron, and the cookie part represents the mass of the atom that's positively charged. And one cookie, one atom, is neutral. And there's just the right number of negative electrons or negative chips in each size cookie to keep them neutral. She didn't make the cookies. Too bad. So we don't have a chocolate chip cookie model. We have this plum pudding model, which is kind of hard to remember, but you got to remember it because it's on the Regents. That's the official name. The name of the Thompson model is plum pudding. Truthfully, I don't like plum pudding. I don't like the idea of plum pudding. It's kind of a dumb name, but the man discovered the electron. We really should give him the respect. He called it plum pudding. We called it plum pudding model. It's kind of like one of those things. Now, ridiculous, all ridiculous. Here is my hero. If I had to pick somebody in chemistry who did it for me, this is Ernest J. Rutherford from New Zealand, had a great accent. Look at that crazy mustache. Crazy. When I went to Europe for the first time in my life, 2 summers ago, a year and a half ago, I went to Italy, which was fabulous, but I also went to London. And in London, there's a very big, famous church called Westminster Abbey. And what's really interesting about that, I'm not a big church person, but I like history and I like stuff like that, but buried in Westminster Abbey are a lot of really cool, famous people in England. And Isaac Newton, the man who invented calculus, I could cry. Isaac Newton was buried there, and Stephen Hawking is buried there, and Winston Churchill is buried there, and Ernest Rutherford. And I got to see the final resting place of Ernest Rutherford. This is it. This is my hero. He figured out so much stuff in chemistry. He won the Nobel Prize, which goes without saying because he was so smart. But he came up with an experiment called the gold foil experiment, which I'm going to tell you about, and you got to memorize because this is, well, he's my hero, and this is what he did, and he won the Nobel Prize for it. He figured out the basic structure of the atom that that look like that little cartoon from yesterday with the electrons flying around the little gold foil. The gold foil experiment. It's maximum important to understand what he did. It's maximum important to understand what it shows. And there's also some flaws in it. And it's important to understand those flaws because those flaws that he couldn't explain, that did get explained later on, forced other scientists also to win more Nobel Prizes to figure out the atom so that I can have a job, so that you can have a class. Why are we here? We could blame it on this man. This man is the reason we're here. This is the man that I have so much to talk about. Here we go. A lot of picture. We'll go really slow. In the center, there's a little piece of gold foil. Now, gold is a metal. It's number 79 on the periodic table. And as it turns out, and you know this, if you take a hammer and you hit a piece of metal and smash it really hard, the metal will squish and get flatter. And if you keep pounding and pounding and pounding, you can make metals flatter and flatter and flatter. Now, some metals are harder. Some metals are a little bit softer. But you can pound metals and they get flatter and flatter. Being able to be pounded flat without cracking, like a glass. If you hit a glass with a hammer, or if I hit my laptop with a hammer, it's going to shatter. But if you hit a piece of metal with a hammer, it gets flatter. That's called being malleable. Malleable is a vocabulary word. Now, as it turns out, of all the metals, gold is one of the most malleable, which means you can pound the hell out of it and it gets super duper thin. So what he did was he says, I'm going to need a piece of metal and flatten it really, really thin. So he got some gold and he hammered it. He probably didn't do it. He probably had some jeweler do it. But the gold foil was so thin and was solid, but it was so thin you could blow it and it would just blow away. And he put it in a little frame so that he could hold it up and keep it right where he wanted to. But this is a cartoon drawing. Thin piece of gold, but still solid. You couldn't see through it. It was made of metal, but super thin. Now, in that box at the top right-hand corner, that's a lead box. And as it turns out, lead's really good insulator for certain things that are, for instance, radioactive. There was a friend of Rutherford's, a professional colleague, Marie Curie, and her husband Pierre, who had discovered a few elements that were radioactive, and they were beginning to understand what is radioactivity. We'll learn about this later in the year. And she had an element that she discovered and named after her home country called Poland. It's called polonium. It's element number 84, PO. And as it turns out, there's a whole bunch of different kinds of radioactive particles that can get emitted by a radioactive element. Polonium emits something called an alpha particle. And alpha particles are not good for you. They're radiation. And what's really weird is they're the largest particle. They're very small. You can't see them. They're invisible. They're the size of atoms. But they're the biggest radiation particle. If they hit you in the skin, they'll bounce off your skin. Or if you want to hold up a piece of paper, they'll bounce off a piece of paper. They don't have a lot of strength to penetrate. Not too much to penetrate, but if you get them in your mouth or your eyes, in the wet part of your body, right? If you cut your arm open, which would hurt, but you shot them into your muscle, you would get radiation poison. You could die. Really bad for you, radiation. But if you keep it in a lead box, the radiation stays on the inside. So in this lead box, Marie Curie said, put them in a lead box, drill a little hole through the lead box, and you can aim the particles, because they'll come out of the polonium, they'll be bouncing around inside. There's a little container space in there. The polonium's in there, and the radiation particles, the alpha particles are bouncing around, and they can only come out through the one hole. It's kind of like a rifle almost, a barrel of a rifle. If they ever find the hole, they're going to go straight through there, and you could basically aim the alpha particles. And Rutherford realized also that there's a certain chemical, it's written, the name's on the bottom right, it's called zinc sulfide, ZNS is the chemical formula. And what's really, there's really cool properties in everything. Zinc sulfide, when an alpha particle hits zinc sulfide chemical in the dark, you see a little spark of light, little, there's my hand, and you could see a little spark of light. So if you set up some polonium in a lead box and aimed it at some zinc sulfide, you would see a little spark of light every so often. And you could count how often do you see it? How many times a minute does it happen? And you could test this over and over and over because the particles, the alpha particles coming out of the polonium come out at a relatively constant rate. They come out of the box at a constant rate. So they might happen 14 times in a minute or 18 times a minute, but whatever, it's going to be constant and you can count it. It's not like 1,000 times a minute where you can't count it. I mean, this was a long time ago in the early 1900s, but they could count it. Get a room in the dark, set up some zinc sulfide on a screen so you could stand it up, aim the alpha particles, and you could count it over and over and over. Then set it up like this and put a piece of gold foil in the middle. Now the gold is solid and the alpha particles you would think would hit it and then they'd hit a solid. What would happen? So what Rutherford did was he set up this screen that was pretty big. The picture doesn't show it. It goes all the way around the box and he shot the alpha particles right at the gold foil. And as it turned out, about 99% of the particles went right through the gold like it wasn't even there and hit the detecting screen straight out on that straight line. So if it's 18 times a minute that you count the little flash, 18 times a minute you still count the flash, and almost every single flash is right where they used to be when the gold foil wasn't there because the alpha particles are going right through the gold like the gold is not even there. And Rutherford said, that's kind of crazy. But every once in a while, he sees a little spark off to the side or even to the reverse. You see that one on the top there? Alpha particle deflected at a large angle. It actually bounced, it seemed to bounce off the gold and bounce back, and it would hit part of the detecting screen kind of behind the gold. It would hit the gold and bounce backwards. And Rutherford was like amazed, like, wow, what the heck is going on? If I could figure out what's going on, I'm going to get the Nobel Prize. I better figure this out. And right here, he has to figure out what is going on. What does a gold atom look like that alpha particles can just go right through them? Mostly, 99% of the time. But every once in a while, they ding off to the side. Oh my goodness, they bounce backwards. What is the shape of an atom? What is the gold atom? How is it built? That was the point. Can I figure out how is an atom built? Now, what did he know? Atoms are neutral because all atoms are electrically neutral. Everybody knew that. Atoms have electrons. And he kind of probably figured atoms are not like billiard balls and atoms are not like cake, plum pudding. It got to be a better idea. Puts on his thinking cap, lets his mustache grow a little, and here's what happens. He says, atoms of gold, all atoms, are made up of mostly empty space. Since most of the alpha particles went right through the foil, right through the gold foil, like it's not really there, must be it's not really there, right? It must be the way the atoms are built. There's a lot of empty space. He said, since atoms are neutral and the electrons are there, he said the nucleus must be dense and positively charged. The alpha particles were also positive and they never seem to stick. They bounce off. So if the atoms were built in a certain way, they'd have to have a dense center that was positive, but the atom was neutral, so he had to put the electrons outside flying around, because then you could have a very dense center that gave most of the mass of the atom, and then you could have these negative electrons flying around the outside, maybe like planets, that could neutralize the positives and negative charge, right? And the center of the atom, which he called the nucleus, he gives the word nucleus to us. He didn't know about protons and neutrons. He just knew it was positive. He knew it had to be positive because the alpha particles were positive. Marie Curie told him they were positive. So when the positive charges hit the nucleus, they didn't stick. They bounced off. That meant the nucleus of the gold atom had to be positive also. And if the nucleus of the gold atom had to be positive and the atom of gold was neutral, where were the negative charges? Where were those electrons? He said, well, they could be flying around the outside, and that would give a lot of space between the nucleus and the electrons. There'd be a lot of space for the alpha particles to go right through. Makes sense, right? And he said, this is kind of like planets. And right around this time, they were coming up with really good telescopes. Hubble was a good scientist back then. They're looking at the stars and the solar systems. Everything's going around. The planets going around the sun. We're starting to understand all that. Planets go around the sun. They never fly away. They never get sucked into the sun. Electrons seem to be flying around. Perfect. Okay? The Rutherford model is called the planetary model. This is what he imagined. In the center, there was a very dense, small, positive nucleus, squashed all the mass together in the center, kind of like a sun. And then there were negative electrons that were just doing all this crazy zooming around, but relatively far away, so that the atom itself had a lot of empty space. And these blue lines that you see, these are what he used to call orbits. We don't call them orbits anymore, but he thought they were like orbiting the nucleus. Those orbits are for you to see where the electrons are going. The atom itself is the nucleus and the electrons. Those lines are just so you can see how much area or space those electrons might take up. But those electrons are super small, and they're not really taking up that space. They could be anywhere in that region, but without those blue lines, the atom would look a lot more like empty space. And it really is mostly empty space. Now, here's the problem. Rutherford says, ladies and gentlemen, let me tell you all about the atom. It's mostly empty space. How could that be? How could that be true? Think about it. If I was made of atoms, and I am, and the atoms that make up my face are mostly empty space, how come I can't stick my finger through my face? If it's 99% empty space, how come you can't see through me? How come I can't walk through the wall? How come I can't even get a little bit into the wall? How could they be mostly not there? That makes no sense. Now, then you're going to tell us, and he did, you have negatively charged electrons that are flying around a positively charged nucleus. How do they keep flying? Don't they ever get tired? Don't they ever slow down? If they slow down, ever, the attraction to the nucleus would make them stick because it's positive and negative, right? How come they never slow down? And if they don't even slow down, how could they never slow down? How could there be perpetual motion? But even if you couldn't explain that, how could they not? How is the attraction not just sucking them together? And how far away are these electrons? Why don't they fly away? Why don't they go to Buffalo? Why don't these electrons, I'm going home, I'm going somewhere else, I'm going over there. How does this make sense? The electrons just keep going and going and going and going, and they never get away, they never get tired, and they never get attracted to the nucleus. How could this be? And he said, you know what? I don't know. But look at my gold foil experiment. It cost almost $50, and it's one of the best top 10 experiments it's going to be for all time. And someday I'm going to get the Nobel Prize for this because, well, he couldn't say that, and he wouldn't say that, but he couldn't answer these questions. But he was right, but he didn't know yet. And that's what's so cool about science. You can do tests and create theories and say, damn, I think this is right. I just can't explain it all. I hope somebody smart comes along. So one of his students actually is going to help him. Now, this man's not a chemist. He's a physicist. So that's why he doesn't have a mustache. He did win the Nobel Prize. I have Niels Bohr. When he won his Nobel Prize, he gave a speech. I have a copy of it. It's right over there, and I read it every year. This man was in the middle of everything. Oh my gosh, is this man smart? I could cry again. He was friends with Ernest Rutherford. He was friends with all the great chemists and all the great physicists. He was so smart. Oh my goodness gracious. And is a plural first name, Niels. That's a cool name. What's your name? Hi, Neil. No, not Neil. Niels. Niels Bohr. And Niels Bohr was a genius. And he was able to prove that the Rutherford model was correct. And this is kind of what he did. Bohr said, yep, we got a planetary model. We got a nucleus in the middle, but the electrons are not just flying around. He said, no, they're in specific orbits. Now, he said that word also, orbits. We don't say that word anymore. Listen to me. 2 Nobel Prize guys in a row make a mistake, and I have the nerve to say wrong twice in a row. I'm on eggshells here, but it's not correct. But at the time, honestly, it's a really good idea. When I was in school, they were still called orbits. When I was in 7th grade, Mr. Smith told me about orbits. It was way easier. It's a little more complicated, but not too bad. I'll tell you about it another day. Maybe later. He said the electrons are in specific orbits. They're not just flying around. And then mathematically, for hydrogen, he proved mathematically that with one proton, hydrogen has a mass of 1, it has 1 proton, has no neutrons usually, it has 1 electron. He proved mathematically, and this is math that I don't understand. This is math that probably 17 people ever understand that are alive. I mean, it's so complicated. But he proved mathematically that the distance apart that the electron was from the nucleus, the charge positive versus the charge negative, mathematically proved that if it stayed in a specific orbit, it could never lose energy. It would never lose energy. How? Well, it's in the math. I don't understand that math, and neither do you. I'm not even going to try to explain it because I don't understand it. It just goes and goes and goes. The attraction holds the electron from flying away, but the speed of the electron is fast enough so that it can't get sucked into the nucleus. It's a perfect balance. And that makes sense because atoms have electrons, and the electrons are far away from the nucleus, and they don't seem to go away, and the electrons are never in the nucleus. He proved for hydrogen that it worked. And even though he was one of the smartest people to ever be alive, he couldn't prove it for any other atom because even with helium with 2 electrons or any atom with more, the math became insanely impossible. But he proved that the electron would not lose energy. It would keep spinning in its orbit. It would not get attracted to the nucleus because of its speed, and it would not go flying away because of the attraction. It was perfect. And obviously atoms are atoms. We have atoms, and they don't all lose their electrons, and they don't all have electrons that squish to the nucleus. He called these orbits also energy levels. And he said that the electron orbits, excuse me, the lowest ones, the closest to the nucleus, the smallest ones, had less energy, and the electrons in higher orbits or higher, further orbits had more energy. So in an atom that had multiple orbits, and again, we don't call them orbits anymore, we call them orbitals. We're going to get to that. Electrons in higher orbits were more energetic than electrons in lower orbits. And he called them shells or orbits, but we call them now orbitals, electron orbitals, but they used to call them orbits, okay? So I already told you it only worked for hydrogen. We're going to draw a picture now, the simple Bohr model for nitrogen. Now, if you find nitrogen on your periodic table, you should take a quick break here, put your finger in box number 7. Nitrogen has 7 protons. It has a mass of 14 AMUs. Now, if you have a mass, I don't have my letters, the protons and neutrons. If you have 14 and take 7 away, because they're protons, that means you have 7 neutrons also. It also, nitrogen, has 7 electrons. You know that because it's number 7, and also because on the periodic table, nitrogen has what's called an electron configuration of 2-5. There's 2 electrons in the first orbit. I'm going to still call them orbits. They're not orbits. And then it's going to have 5 more electrons in the second orbit. This is a Bohr model or a planetary model for nitrogen. And you can do this. You're going to take a break in a second. You're going to copy this because you have to. In the center, you're going to draw 7 circles that have little pluses, or they're going to fill them in. They're going to be the protons. You're going to have 7 other little circles that don't have pluses. They're going to be neutrons. They'd be either, you can make one filled in and one hollow, but you can have 14 little particles stuck in the middle. And then you're going to draw the first little orbit that goes around. The first little orbit has 2 electrons in the first orbit or the first shell. And then there's going to be 5 electrons that are going to go around the outside because that's a higher energy level. And the atom of nitrogen, 7 protons and 7 neutrons squashed into the nucleus. And then there's 2 orbits, orbitals, but 2 orbits, 2 and 5. So there's 2 electrons fit in that first baby-sized orbit. It's the smallest one. And then the rest of the electrons will fit in the second orbit because the second orbit, it can hold up to 8. So you could fit 10 electrons in 2 orbits if you wanted to, but we only have 7. So 2 are in the first, fills it up. The rest go into the second orbit. We don't need a third orbit here or a third orbital because we don't have enough electrons. They fit in 2 and atoms try to stay small. They are small. All right. Niels Bohr, not only did he figure this all out, he also said some other cool stuff to get him a Nobel Prize. He said that electrons, if you zap them with electricity or with heat or something like that, you could give them a unique amount of energy, and every single atom has a different number of protons pulling in and a different number of electrons flying around in different orbits. He figured that you could give any atom or any electron in any atom a unique amount of energy, and you could get it to jump upstairs to a higher energy level, because the only difference is that the electrons in the smaller orbits have less energy than the electrons in the higher orbits. But if you zapped it with electricity or you zapped it with heat or radiation, you could get one of those electrons that's in the normal low energy level called the ground state. You could get it excited. Kind of like if I were just talking and I started drinking a big cup of coffee, in a little while I'd be talking like this. I'd be all excited. The caffeine would be going through me. I would still be myself. I'd still have all the same parts, but I'd be excited. Atoms are normally in the ground state. The electrons are in the lowest energy levels possible. But if you get a unique amount of energy, if you get energy in a certain way, you can get excited. In electrons, you still have the same number of electrons now, but one or more of them is in a higher energy level because they've absorbed this energy and they're all excited now. And then what he said, which was the coolest thing, and you're going to be able to see this in the next lab, the electrons lab that'll be coming up soon. Once you excite atoms and the electrons get excited and jump to a higher energy level, when they return to the ground state, they're going to emit that unique amount of energy. And you could see it with your eyes. It comes out as a color. So cool. And every single atom makes unique colors. So you can zap an atom. Well, you have to do more than one. One is too small. But if you have, say, a tube of neon gas and you electrify it, all the neons that have an electron configuration of 2-8, they all get a little excited. It becomes, say, 2-7-1. One of those electrons jumps to a higher orbit. When it returns back to, instead of being 2-7-1, it goes back to normal. It goes back to ground state. It goes back to 2.2-8. In order to go back to the ground state, it has to release energy. And that energy it releases comes out as a color. And you will see it. And if it's neon, it only comes out as an orange color. And you can see it with your eyes. And since every atom is different, unique, every atom has a different number of protons in the center that are pulling on the electrons and a different number of electrons that are flying around, in order to excite any atom, it takes a unique amount of energy. And it releases a unique amount of energy when the electrons go back to the ground state. And you could see it. It's freaking incredible. It's so incredible. Now, the excited state is when the electrons are not in the ground state. On the periodic table, all of the electron configurations are ground states. When they get excited, it's the same number of electrons, they just at a higher energy level. When they return to the ground state, that's when they emit this unique amount of energy, and it comes out as a unique color you can see with your eyes. Freaking fantastic. Now, I said all this already. Maybe you knew that. The important thing is it's the same number of parts. Each atom is made of stuff, protons, neutrons, and electrons. When they're in the ground state, the stuff is in a stable, low energy state. When you zap it with energy, they get excited. It's the same number of parts. It's just they're in a different place. And when they return to the ground state, they emit this unique energy, and this energy is called spectra. That's what it's called. When you see a neon sign that says open, the color of light coming out of that, we call that light spectra. Now, sometimes you see signs that say, I don't know, bagels, and it's a blue light. And you would probably say, oh, look, it's a blue neon sign. No, 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 no. Neon is an atom, and it's unique. And neon gives off a unique color, which is orange. If you see a blue sign that says bagels, right? Because you've seen gas signs, you call them neon signs in different colors, but they're not. Different atoms give off different colors. Argon gives off a bluish color. So does water. All kinds of gases give off all different. Sometimes you can mix gases and get mixtures of colors. Neon only gives off orange. Other gases give off other colors. Neon lights are made of neon gas. When neon gets excited, the electrons go to a certain excited state. When they return to the ground state, they release a spectra that you see as orange. If you see a bagel sign that's coming out in blue, if it's not orange, it's not neon, it's a different gas. You just call it a blue neon sign or a green neon sign. No. Neon only gives off orange light. And that light we see with our eyes is called the spectra. How cool is that? Now, the modern model, we're finally to the last model. So after Rutherford tells everybody what the atom looks like, and Niels Bohr proves that he's right, even though it's kind of wacky, the math, but some really smart people say, yep, he's right, and we all agree to that. The modern model has taken a lot of people to do a lot of funky math, and the mathematics is way out of the scope of this class. Don't worry about it. But this is important, number 52. This is on the Regents almost every year. The modern model of the atom has been developed by many scientists over a long period of time, since Democritus, 2,400 years ago. For 2,400 years, with Democritus, Dalton, Thomson, Rutherford, Bohr, and hundreds of others. I mean, Marie Curie and Pierre Curie for doing that. James Chadwick discovered the neutron. We don't even mention him in this class. Yeah, I mentioned him, but he's not even in the curriculum. There's so many people. Wolfgang Pauli and Heisenberg. There's a funny joke I'll tell you another day about Werner Heisenberg. There's so many people. Einstein and so many more. Many people. Now, the modern model is called either the modern model or it's called wave mechanical because it's hard to remember. Wave mechanical. And that's because the electrons sometimes act like waves of energy, or sometimes they act like little mechanical bits of matter that spin around with a negative charge. Now, this is a really weird thing. Sometimes in science, things are hard to understand. And this is one of these deeply complicated, almost existential, how the heck can we ever make sense or understand this? And some people say we can't, it's magic, it's God, it's a lot of things. Or we have to sort of accept the complexities and do our best at any moment to say it's kind of like this and it's kind of like that, and even though these are two different things. Electrons are funky, completely funky. Sometimes they act like waves of energy, and sometimes they act like little bits of matter. And that's just the way it goes. And so we call it the wave mechanical model. And this model is more about not exactly where are the electrons, but where would they probably be most of the time. Most of the time. Because they're not always going to be where you want them. They're not always going to be where you expect them. They do whatever the heck they want. Now, this is the last slide. This is number 55. Now, this diagram, don't even look at the words. Look at this picture. This is a comprehensive kind of a diagram. In the center is the nucleus of a helium atom. Now, a helium atom has a mass of 4. There's 2 protons in there, and there's 2 neutrons, packed tight. Around it is that dark ring. Now, a helium atom also has 2 electrons. Now, what this diagram sort of represents, imagine if you had a special camera, which you can never have because helium atoms are too small. But if you took a picture of a helium atom and you could take a picture of it and you could see it, you can't. But if you could imagine this now. The nucleus is in the center, and any 2 of those black dots around the outside ring, any 2 of them would be the 2 electrons. There's like 5,000 dots there. Just imagine a little nucleus and 2 dots. That's one photograph. Then you take another photograph. And the electrons are moving, so they'd be in a different place. And then you layer those 2 pictures together. Then you take another picture and another picture, another picture. And you start layering and layering and layering pictures. What you're basically going to have is the nucleus is going to kind of not move too much. Maybe a little hum, and that's why it's a little moving there. But where are the electrons now? Where are they now? Where are they now? Where are they now? They keep changing places. They're moving, they're moving, they're moving, they're moving. But if you take 1,000 photographs, or 5,000 photographs, or 10,000 photographs, and you can somehow magically layer them all together, what these dots represent is where are the electrons most of the time. And the darkest areas are where the electrons mostly are, and where it's not as dark, that's where the electrons are sometimes. And where it's really light, like really to the far outside, there's just a couple of random dots out there. Only once in a while would the electrons get that far away or that close to the nucleus. But electrons are kind of wackadoo. They do anything they want. They go over here, they go over there. They move fast, and then they get far away, and then they come back. Statistically, from a statistical examination, they could literally be anywhere in the universe. Now, it makes no sense that an electron in an atom right here could be in Buffalo and back in a flash, but that's true, all right? According to the mathematics of physics and chemistry and quantum theory, electrons can actually, in a sense, disappear and be somewhere else and come right back in instantaneously. But statistically, let's not get too far out there. Statistically, they're kind of usually in the zone, and that zone would be the first orbital. The 2 electrons in the first orbital of helium they're right there. Sometimes they get a little further away, sometimes they get a little closer in. And this diagram shows wherever it's the darkest ring, where the probability of the electrons are going to be greatest. But sometimes they get close and sometimes they get far and sometimes they go to Buffalo. Sometimes they go to the other side of the moon. They come back. Now, I can't explain how that is true, but it's true. Mathematically in quantum physics and quantum chemistry here, it is true. They could be, the 2 electrons in helium could be anywhere and then they come right back in an instant. And that's crazy. Electrons are like teenagers, right? It's 4th period, let's make believe. 4th period, you're all supposed to be here, but somebody is home. This year, it's even crazy. Most of you are home. But if it was a regular year, I would say, there's 23 kids in this class. If I bet you all $1 a day at this exact time, you're going to be right here in this room, I'm probably going to win the bet most of the time. Now, sometimes somebody's got a dentist appointment. Sometimes at this exact time, somebody's in the bathroom. Sometimes somebody's cutting school. Sometimes somebody went on vacation with their family. But statistically, you're always going to be where you belong most of the time. So most of the time, the electrons are in this dark cloud. Most of the time, they're right where you expect them to be. But statistically, could be a lot of other places. But most of the time, the electrons are where they're supposed to be in this orbital. It's not in orbit anymore. See how it's like a fuzzy zone? It's in orbital. That's the difference. They're no longer a single unique radius around the nucleus. They're kind of really fuzzy, close, far, really far back, but they're mostly in what's called an energy level or an orbital. But occasionally they get away. Okie doke. This is a little longer. We just did 2,500 years of history. Really cool, really a lot. Ernest Rutherford is my hero. All right, thanks for watching this one too. Bye-bye. I'm going to stop recording.